Welcome to Hydro-Dyne Engineering's live webinar series. In this session, I will be reviewing MBR screening challenges and solutions. We'll be running a live Q&A at the end of the webinar, so we have enabled Zoom's Ask a Question feature. It's at the bottom of your screen, so just click on that, enter in your question, and we will review the questions at the end of the presentation. Off camera, we have Jay Conroy, who will be monitoring your questions and helping me field your questions, and we'll attempt to get in as many as possible. Also, at the end of the webinar, we will ask you to provide some feedback by completing a short survey. That feedback is very important to us because it helps us improve and ensure that we met your expectations. I am Randy Dow, the Sales Director for Hydro-Dyne Engineering. I have over 25 years experience in the water and wastewater industry, including supply of MBR systems with MEMCOR and Cope membrane systems. So during this session, we'll be reviewing the application challenge and technology options, MBR design lessons learned, Hydro-Dyne solutions for MBR screening, reviewing a couple of application case studies, and then we'll get to Q&A. So let's first look at the unique application challenges of membrane systems. And I'm really going to get basic here. We have a wide range of audience. I appreciate everybody attending. So we'll get down to some of the basics for MBR systems. So MBR treatment processes require ultrafine screening with openings less than 2 millimeters. Most of them are 2 millimeters. Some of them go with 3, but predominantly it's 2 millimeters or 1 millimeter openings. And the reason for that is because you want to reduce the size and the quantity of particles that are entering the membrane tank. Unlike clarifiers, once debris gets into the tank, there's no place for it to go. All the filtration occurs in the membrane fibers, so any solids that get into the tank stay in the tank. And that not only includes solids, that includes hair, fibers, other things. On the MBR site, they've cited that for every 1 milligram per liter of debris equals 8.5 pounds of material per million gallon per day. So you can see over a period of time, you're going to build up a lot of debris, even with a very small amount of debris entering the tank. Membranes are also extremely sensitive to hair and fibrous material. So you look, I've included 2 pictures on this slide. The top slide is a clean membrane bundle. That's exactly what you want the membrane bundle to look like after years of operation. It's free of debris, free of hair, nothing is matted on the inside of the bundle. The bottom one is a heavily fouled membrane bundle. That has hair, it has fibers. You can see that it really is choking off the membrane bundle. So here's what happens. So you have the debris that enters the membrane fiber bundle. And that debris tends to collect, especially for membrane fiber bundles that they have a top potting made of polyurethane. So as that solid builds up in that fiber bundle, it prevents the re-wetting of the membrane fibers. And when you prevent the re-wetting of the membrane fibers, they ultimately can dry out. When they dry out, they become what's called irreversibly fouled. So now you have some membrane surface area that's irreversibly fouled, and now that's not available for filtration, reducing the overall filtration capacity of that membrane system. So it's very, very critical to keep that debris out of the membrane bundle. If debris does get into the membrane bundle, then typically that requires removal of the membrane cassette and manual cleaning or power washing of that bundle, which is what the person is doing, starting to look at in this membrane bundle. Presence of debris ultimately creates risk. It creates risk for the owner. It creates risk for the membrane supplier. Most membrane operating systems require a 10 to 20 year guarantee on the membrane performance. So as you can see, any debris that's entering the tank poses a risk to that guarantee. So now let's talk about technology options that are available to address that solution. Membrane screens can be placed in various locations. They either can be placed at the headworks of the plant if you don't have a primary clarifier, or right before the membrane system. That typically requires a coarse screen in front of a fine screen. The coarse screen typically is around 6 millimeters. The fine screen is around 2 millimeters. Other designs for larger plants have the membrane screens right after the primary clarifier, and that's an advantage because the primary clarifier is another unit process that will remove a lot of that debris, thus reducing the load on that membrane screen. So when you look at the screens, the two options are primarily center flow band screens and drum screens. In the early 2000s, center flow band screens really fell out of favor. They were provided for initial MBR systems, but those initial designs often were undersized, and so they could not handle the peak capacity, or they allowed a lot of debris leakage through the screening system. As a result, center flow band screens fell out of favor, and the industry now has really adopted use of drum screens, either horizontal drum screens or inclined drum screens as the screening system that they prefer. But those type of screens, the drum screens, are not without those limitations as well. So now let's look at a comparison of drum screens versus center flow band screens. So with drum screens, but the advantage of the drum screens is that they are very efficient at screening capture. Horizontal drum screens have very, very high capture rates. Inclined drum screens have somewhat lower capture rates. They're self-contained. What I mean by that is that as the debris is removed, that debris is deposited typically in an auger, and that auger removes the solids from inside the drum. They also have zero carryover. So when the debris gets in the drum, if it's not completely removed, then it just rotates around the drum and is removed the second time around. So you don't have any carryover, any bypass of the drum screens. And finally, drum screens are a known commodity. There's a lot of installations out there, a lot of references, and so when a client or an engineer is looking at an MBR design, they have a lot of different reference installations to refer the customer to. So let's look at the disadvantage of drum screens. The primary disadvantage really has to do with its operational flexibility. Drum screens require wider tanks and shallower depths. Their maximum operating level is typically less than half the diameter of the drum. And so especially for larger plants, if you need to design more capacity into the system, you're adding more channels and more drums, which is shown in the bottom picture right here. This is a plant that has multiple inclined drum screens and multiple channels. So if you have wide range of flows, you're going to be bringing channels online and offline. And so from an operational standpoint, it just creates a lot of challenges for the operators. Also, they can be difficult and costly to maintain. Some drum screen designs have bearings in the inside the water. And so when those need to be inspected or replaced, you have to remove the drum screen from the water. For horizontal drum screens, they will require sometimes a ladder for access or a platform for access or maintenance. The advantage of the horizontal is that all the components are above a channel. So that reduces the complexity. If you look at wide channels and you have a wide variation in flows, that also provides some challenges when it comes to grit deposition. So at the lower flows with wide channels, the channel velocities go down and the grit can settle into the channels. And then you get a peak flow event, all that grit is picked up and deposited inside the drum. And lastly, the drum screens, because they need to be fitted in a wider channel and a shallow channel, may not be the best option for retrofit. So now let's look at center flow band screens. The advantages of center flow band screens is similar to drum screens in many aspects. They have zero carryover and they're very high capture screens. We like to refer to them as elongated drum screens. So when the debris gets into the screen, it can't get out of the screen. It has to stay in the screen and be deposited and discharged into the center of the drum or center of the band screen. And I'll show, we've got a good animation that shows that. So there's zero bypass, zero carryover type technology. The biggest advantage is the design allows use of smaller width, deeper channels to handle a wide range of flows. So for larger installations, you need narrower channels, fewer channels, and overall lower footprint. And because of that ability to operate in deeper channels, you have much greater operational flexibility. So from a disadvantage standpoint, as I mentioned before, there still are many screens out there that are not designed with good sealing. So you will have debris leakage through the grids or around the grids. Additionally, you have the market perception because there's not as many good center flow band screen installations and the preference for drum screens. There are some really good ones. We'd love to provide you our list of reference installations. But the fact that we have a limited number of installations makes it difficult for customers and engineers to view. So I talked about flexibility in design. What we created here is a table that really shows the difference in how you can design center flow band screens to meet the specific channel width and depth that you're looking for your design. So I have in a table here what we refer to as a tall and a short screen. A lot of the parameters are the same. 25 MGD is the peak flow rate. You see the channel width for the tall screen, it's a 44-inch wide. The short screen has an 108-inch wide channel. Channel depth for the tall screen is 140 inches. For the short screen is 70 inches. One of the keys are the design parameters for velocities. You see in both instances, key design parameters are matched. So the key design parameters are the throat velocity, that's the velocity going into the center of the screen. We have the grid velocity, which is the velocity going through the grid, and the recess velocity is the velocity coming through the grid and outside and back around the screen. So you can see in each case, they're ideally matched. What that results in is very similar head loss, about 8.5 inches. One screen under that operating condition is operating at an upstream water depth of about 118 inches, and for the short screen, it's only operating in an operating depth of about 4 feet. So how do the two screen designs then compare? For the screen size for the tall screen, the width is the opening of the screen as the flow goes into it is 28 inches wide. The depth, that's the depth of the screen in the channel, is 36 inches, and the height is 212 inches. For the short screen, you see the width is almost 5 feet, the depth is only 6 feet, and the height is about 70 inches less than the tall screen. So we sometimes have engineers contact us and say, hey, I need a 20 MGD screen. Tell us what be the optimized screen type and screen approach. And we say, can you give us some information on the channel dimensions? This is why we ask that, because we can design a wide range of sizes based on your channel preferences. In this case, I also want to highlight is that the short screen is about 2 times the cost of the tall screen. So you can really make a big difference in your design based on your assumptions of channel design. So now I'm going to review some screening best practices, some lessons learned. And these we've derived from our experience in retrofitting other screening systems and our experience from designing new systems, not only for MBR plants, but also for any plant where we need ultrafine screening. The first thing is the grid selection. These first 2 bullets about dual stage screening, and primary clarifier screening identify the opening sizes, but what I want to emphasize is for the dual stage screening, we're recommending using a high performance, high capture, 6mm center flow screen. I'll touch on that in a little bit. The next one is the use of VFDs, variable frequency drives. They increase the flexibility of the system by allowing you to increase and decrease the grid speed. So during peak flow events, you can increase the speed of the grid, more rapidly removing solids to maintain the optimal head loss across the screen. When the flow drops below the peak, you can slow down the screen. You can increase the capture, improve the life of the equipment. Next thing is to recognize that not all sites, not all plants have the same waste stream characteristics. I'll touch on that a little bit more in a few slides, but essentially if you have questions about the characteristics, that is the quantity and size of the debris in your waste stream, our recommendation is to do some on-site testing because not all core screens should be 6mm. In some cases, we've learned that we need to go down to 4mm for the core screen, just because of the small size of the debris that's entering the system. The last item is redundancy, and that's the key. You have to make sure that you have redundancy in all components, not just your screens. A lot of screening systems have an M+1 design, so it could be 2+1 channels or 3+1 channel. But what you need is redundancy in all the components, the screens, the solids handling system, the control panels, everything that if one fails, the other one can pick up the full load for the system. So the next two slides touch on the common pitfalls that we've seen. One of the biggest one is undersizing the equipment. And the key here is the blinding factors. Blinding factors need to match the influent waste stream. So what we typically use for post-clarifiers is a blinding factor of about 30%. In some cases, based on the number of unit processes upstream, we can even go down to 10%. For dual stage screening, we ideally want to use 50% blinding for both the coarse screen and the fine screen. Our desire is that each screen removes about 50% of the load. And if there is no coarse screening, we typically default to at least 75%. In some cases, we go up to 85, 90%. So if you have no coarse screener, if you have insufficient coarse screening, you're going to have some very large ultrafine screens. As I mentioned before, what you need to do is to make sure you understand what size coarse screen is used. So the coarse screen openings typically don't consider the waste stream characteristics, as I discussed previously. The next area is similar to the grid opening, and that's the insufficient pre-screening. Not all 6mm screens are alike. I'm going to touch on the UCWEAR test report over in the UK, where they tested 65 different types of screens. And if you look at the information from that report, on average, multi-rake screens and step screens remove about 35% of the debris, while center flow band screens at 6mm openings remove 84+% capture. So you really need to understand what type of technology you're using, because that's going to determine how much debris that coarse screen removes, and therefore how much demand is going to be on your fine screen. Another area to consider is the freeboard. Most plants have a standard 18 inches to 2 feet of freeboard. For ultrafine screening systems, in all cases, we're really estimating what we anticipate the blinding factor is at peak design conditions. But in some cases, you may have transient operating events where it increases that blinding rate higher than what you use for the design. So what that's going to result in is that's going to result in higher head loss. Higher head loss means you're going to increase the upstream level in front of that screen. So you want to make sure you have sufficient freeboard, so in case of those transient events, you'll have that freeboard so you don't run into any operational issues. Lastly, I mentioned the redundancy for all components. Again, that's a key one. If you can't have redundancy in the components, what you may have is extra storage capacity. That will provide you for peak flow events. If your system can't handle it, then you can store the waste until the peak event subsides, and then you can process the rest of it through the system. So here are some additional common pitfalls. I want to show another picture we have. This is a membrane system that has excessive sludging. So there's just excessive debris that came into that plant, and you can see, as I explained before, look where it's all congregating. It's all congregating at the top of the membrane bundle. So that's an example of something we don't want to see. So next I want to talk about how some screen designs don't take into account the maximum static and dynamic differential. So what do I mean by that? So if you think about the screens and they're operating, there could be situations where the screen gets shuts down, loss of power, some issues with the controls. The screen shuts down. If the flow continues, that screen grid becomes immediately blinded. As it becomes blinded, the level of upstream of the screen increases to the point where it overflows, hopefully a bypass weir to prevent it from coming out the channel. And downstream, if there is no weir or there is no downstream process that maintains the minimum level in the channel, the downstream level can drop to 0. So if you have an 8-10 foot deep channel, now you have 8 foot in front of the screen, you've got 0 behind the screen, you've got an 8 foot differential. Well, the screens need to be designed to handle that differential. Similarly, if you have that situation, you need to make sure that you can start up the screen. In that situation, you can start up and operate it to get it back running. Next one is the insufficient screening handling design. As I mentioned, redundancy. Here, designers need to understand that most compactors typically handle dry offload, maybe have some spray wash offload as well. When you have complicated screening systems with coarse screens and fine screens, that solids handling system needs to handle not only the increased solids load from both screens, but it needs to handle the volume of wash water. Then the volume of wash water is where, at times, the solids handling system is undersized to handle all that wash water. So you need to make sure that design has capacity for high solids, high wash water. You need to take into account the discharge location. Is it going to be close to the screens, or at a long distance you're going to have a sluice which will add even more water? Lastly, I want to talk about unloading and loading. So when the screens are loaded, you have to have an effective way of offloading them. Some manufacturers use brushes. We prefer not to use brushes because they provide insufficient and cleaning of the grid, and they don't last a while. They have a lot of repair and maintenance issues. So we focused on spray bar. We have 2 spray bars that offload the screens. The key there is the operating pressure and wash water volume. So you need to make sure you have sufficient wash water and sufficient wash water pressure. And you need to take into account, if there are situations where you have more than 1 screen operating at a time, then your pressure needs to be maintained even at those higher flow rates. As an example, for our 25 million gallon per day screens and compactors, we need about 100 gallons per minute at 60 PSI. So I spoke previously about the waste stream impact on screen performance. So let me talk about some specific examples here of what I mean by that. So all waste streams aren't the same. There's a lot of different constituents that can go inside that waste stream before it hits the headworks of a plant. In some distribution systems, you have grinder pumps in front of the lift pumps to reduce the size of the debris and prevent from clogging up the impellers. You also have industrial contribution, which is typically smaller size debris. The industry is really being challenged with flushable wipes, and the presence of wipes then can tend to be a problem in terms of how quickly that grid can blind. Some plants separate out their septage receiving. Other plants allow the septage trucks to dump in front of the headworks, and that septage waste stream has different characteristics than a typical waste stream. You also need to take into account, is the waste that's coming to your plant, is that primarily gravity flow where you're going to have larger solids, or is it pump flow where you're going to have smaller solids? You also need to take into account the volume and size of the grit. And I mentioned about the pre-screening. How effective is that pre-screening before you get to the ultra-fine screen? And lastly, your system could have to handle fats, oils, and greases. So all of these can occur in your system, so you need to understand that. And the good news is we do have mitigating options that you can use for those specific type of instances. I'm not going to cover each one. If you have a specific example, please contact us and we'll be glad to discuss your specific situation. So let's look at some techniques that are used to assess screening efficiency. So I mentioned about the UCWER report. That's the UK organization that tested all these screens at the same treatment plant. So it provided a good way to compare different screens on the same waste stream characteristics. But really that's where it stops, because that only applies to that one plant and to that one way that those screens are being operated. So it's great from an initial comparison, or maybe specifying a minimum capture rate, but it really doesn't indicate the capture rate for your specific plant. The next way is a simple sieve test, and that's traditionally a pass-fail test. You take a volume of your waste stream, you pour it through different opening size grids, you look inside the grid, you weigh the amount of solids that are being removed at each different grid size, and then you kind of zero in on, okay, which one is the optimal grid size for us to use in an application. The other method of assessing your waste stream characteristics is on-site testing. And Hydro-Dyne has an on-site testing system where we can come out, do a series of test runs to evaluate your waste stream and provide good information on your characteristics. And lastly is what I call the litmus test for membrane systems. And that's where after a certain amount of operation, 6 months, 12 months of operation, you physically remove the membranes from the membrane tank. You inspect them to ensure that there's not a buildup of debris on the membranes. If there is, then you still have time to address that beforehand, before that buildup of debris impacts your membrane system performance and ultimately the warranty. So now let's look at Hydro-Dyne's solution to address the membrane screening challenges and address some of the pitfalls that I've discussed already. So who is Hydro-Dyne? Hydro-Dyne is primarily a headworks system engineer and manufacturer. We only focus on headwork systems. We're located in Clearwater, Florida. We've got a facility, 100,000 square foot facility here in Clearwater, where everything is done under one roof, all the way from application engineering to design engineering, production, purchasing, quality assurance, final testing. We even have in-house passivation tanks to passivate our stainless steel. We focus on continuous improvement, and we'd like to advance the technology, screening technology, grit removal technology with our systems. As I mentioned before, our screens have been independently certified to 93.25%. That's our 2mm center flow band screen. We focus on exceptional reliability, exceptional performance, long-term performance, and we have in the industry some very, very low costs of maintenance. And finally, we've got a wide range of installations worldwide. So I mentioned before about the animation for our center flow screen. So here's the animation. I want to walk you through it for those that have not seen a center flow band screen design before. So first I want to orientate you. The screen is rotated 90 degrees. So the opening of the screen is perpendicular to the flow, which makes the grids parallel to the flow, which is different than a majority of the screen designs that you see where the grid is perpendicular to the channel flow. At the back of the screen is a plate, and that plate is a diverter plate that diverts the flow inside the screen out both screening panels. So right there you see one of the major advantages of a center flow band screen, and that's the fact that you have 2 times the grid area that you would have from a through flow band screen. Also, what that does is it creates a lower head loss and a higher capacity screen. One other thing I want to touch on is an area where you really want to make sure you have good sealing, and that's in these inlet diverter plates. Our inlet diverter plates do not use neoprene seals or any rubber seals. They're actually bolted to the channel wall. They're bolted and grouted to the channel wall so there can be zero bypass around those diverter plates. So you can see the debris is collected on the grid as it lifts up to the top of the grid. It's offloaded via 2 spray bars. Those spray bars, as I said, were operating at 60 PSI. And then those spray bars right here, they drop into either an integral compactor or to a discharge sluice. For our screens, we'd love to show you more information on our screen design, love to show you information about our sealing. Just to tease you a little bit, I do want to show you our chain, and I want to show you just briefly how our chain is sealed. So this is our chain. That does not look like any other chain that you see on the market. This is a solid piece of ultra-high molecular polyethylene. And you can't see it. We have more detailed pictures, but there's a groove that's machined into this. That groove interacts with the frame, and it's that interaction that creates a 0.5 millimeter seal. So contact us. We can provide you a lot more details, not only of that, we can show you our grid-to-grid sealing. We can also show you more details about our drive system. We'd love to share that with you. So our system is characterized by robust performance, overall lower operation and maintenance costs. I would challenge anyone to put forward maintenance costs, long-term maintenance costs that's lower than Hydro-Dyne's. We've evaluated that over 20 years. We have very few wear parts that are required to replace over a 20-year period. And so it's exceptionally low maintenance. All of our maintenance is done above the channel. All the maintenance is done in this upper section. This is where the seals are greased, where the bearings are greased. The motor oil is changed. You have access panels up here, and those access panels are where you can actually look at the spray bars, make sure the nozzles are working properly, but all that maintenance is contained up there. There's no rotating components in the bottom of the channel, so there's nothing that you have to go into the channel to maintain or replace. Like other center flow band screens, the design results in higher flow rates and smaller footprints because of the hydraulic advantages of center flow band screens. And then additionally, we are a custom engineered company. So all our screens are custom engineered using standard components. So we design our screens for the specific application. So let me now look at some of the ways that we have used different grids and different opening sizes to meet these challenges. So when we look at our screens, when we talk to customers, we like to emphasize that one size does not fit all. So for specific membrane screening, we can have opening sizes between 0.5 millimeters to 3 millimeters. We've designed screens from flows ranging from 100,000 gallons per day to over 100 MGD, and that's 100 MGD per screen, Screen widths as narrow as 2 feet up to and exceeding 6 feet in terms of widths, and screen heights as low as 5 feet to over 60 feet tall. So you can see that's a wide range of custom engineered designs to fit the specific application. Not only can we provide different size screens, different grids, openings, but we can also provide different grid options. So on the far right, we've got the ultra high molecular weight polyethylene. This grid, again, is machined in our factory, just like our black chain, what we call our guide links. That's all machined in our factory. This perforated plate typically is anywhere from 3 millimeters and up in terms of opening size. We typically use that for the core screen. It's a thicker plate, 9 millimeters. We use that to minimize hair pinning that would occur on the thinner stainless steel plates. That's one reason why we don't require a rotating brush. Also, we have the perforated plates, which are used for the ultra-fine screening. So this we will provide in a 1 millimeter or 2 millimeter for final screening or for other specialty applications. And then for a lot of our water plants or other types of applications, we use a woven wire mesh. And we can, again, provide any size opening for any one of those sizes. So that's a quick overview of Hydro-Dyne, showing how we can customize solutions for you. Now I'd like to touch base and finish up with a couple of case studies. The first case study is Canton, Ohio. It's the largest MBR plant in North America. It's a Kubota membrane system, and the total plant design capacity is 88 MGD. So this plant is designed with 3 channels. It's a 2+1 design. Each channel handles 44 MGD. So we supplied 1 core screen and 2 fine screens for each channel. Core screen had a peak design of 44 MGD. Each fine screen has a peak design of 22 MGD. This is one of those installations where an example that a 6 millimeter grid was not the appropriate grid size. So ultimately, we provided 4 millimeter grids, and that provided the right balance to remove the right amount of solids to ensure that we didn't overload the 2 millimeter screens. This solution also has use of the VFDs, as I mentioned, for the core screen and the fine screen. That control program is also tied to the influent flow meter that allows those screens to anticipate when we have an increase in flow so that they can increase the grid speed. Also, our control system is tied to the influent gates for the different channels. So when the demand increases, a signal will automatically open the influent channel gates as well. So the operators like it because they don't require much attention at all. It just runs smoothly and requires very little attention. From a performance standpoint, we had to pass sieve testing that was required by the specification, and we passed it in excess of 95% screening capture. So a very, very successful performance. From a debris removal standpoint, we were removing, with the new system, an average of 6 cubic yards of screenings per day. And as I mentioned, the screen system is automatically operating under a wide range of flows from around 25 to 55 million gallons per day. So the next case study is really the opposite. This is one of our very, very small ultrafine screening systems that were provided in a tank. It's a 1 MGD plant. We provided two screens in separate tanks. So we have that capability as well. If you don't have room on site, you want a solution that can be created and really dropped anywhere on your site, an in-tank ultrafine screening would be one option for you as well. What this makes this plant unique is these screens were outside. In the upper left picture, you can see how this is during a very cold season. You can see that screen. There's no ice, no snow built up on outside the screen. It has exceptional freeze protection system with heat blankets and heat tracing. As you can see, the surrounding pipes didn't have as much insulation and heat tracing, and therefore the ice and the snow were built up on those pipes. That system was for Suez GE membrane system. So let me summarize really some of the key highlights from the presentation. I hope by now that you really have a good understanding of why membranes require effective, reliable, and robust screening protection. Not all waste streams are the same, so we can bring to bear on-site testing to optimize the screen size and, more importantly, reduce the risk to the membrane manufacturer and ultimately to the client. Your screen supplier needs to understand and address the common pitfalls in screening system design. That's something that we can work with you on. We can work on multiple design options. We're very flexible because we have all the design engineering in-house, so we can discuss several different configurations for your solids handling system, whatever you need in order to fit your footprint or your customer's requirements. Our screens are designed to minimize debris leakage, and that is really a key element of how our screens really differentiate themselves from others in the market. Our screen, our Hydro-Dyne Great White Shark, being a center flow screen design that offers the same advantages as other center flow screens, hydraulic advantages, footprint advantages, and because of our robust screen design, we have operating and maintenance advantages as well. And again, and to summarize, our center flow screen will provide that maximum membrane protection. So thank you for joining us today. As a reminder, we would appreciate your feedback by completing a short survey at the end of this webinar. If you have any project or would like to discuss any of the webinar content, again, contact us. We'd love to show you details of how we create our sealing system, not only between the grid and the frame, but the grid to grid. Love to have you pose as many questions as you have for us. You can contact us at www.hydrodyne.com. That's our website. Or email us at info@hydrodyne.com. You can also find us on social media at LinkedIn, Facebook, and Twitter. So now it's time for question and answer, and I'm looking forward to this. Again, my panelist, Jay Conroy, there has been monitoring the questions coming in, and Jay, you want to join me now? And
yeah, Randy, great presentation. A lot of good information conveyed there. I hope it was useful to our attendees. We've got a few questions that came through, and I'll read those off, let you answer them, while hopefully a couple more come through, and any that we don't get to, we can pick up afterwards and address people privately. The first one, and I like this question because you mentioned variable frequency drives a couple times, and they ask, what do you recommend using a VFD for the fine screen drives?
Yeah, that is a great question. I touched on it briefly during the presentation. So really 4 key areas of why you want to use a VFD. First one is operational flexibility. As I mentioned before, you are only going to estimate the screening capture rate. So at peak operational flow rates, the debris is going to come in faster. You want to be able to increase that grid speed. Increasing grid speed removes the solids faster. and keeps the head loss across the screen within your design parameters. When you're not operating at peak design, then you can slow that grid down. Therefore, you want to be able to coordinate that. For a dual stage screen design, you want the screens talking to each other. So if you need to, if the load on the fine screen, the ultra fine screen is too high because the head loss is increasing, you can slow down the core screen. You slow down the core screen, that's going to remove more debris, and that's going to reduce the load on your fine screen and vice versa. So it does give you a lot of operational flexibility using a VFD. The other area is wear life. So our screens are designed, the wear that occurs on our screen or any screen really is based on the number of times that grid revolves around the system and wears those components over the life of the screen. So the screen doesn't know whether you're operating for very low speed for a long period of time or high speed at a short period of time. So what you want to do is during the non-peak flow periods, you want to be able to slow that grid down. You slow that grid down, you reduce the amount of wear on those components, you make them last longer. Next thing is screening capture. Again, when you're not at that peak flow event, you can slow the screen down. When you slow the screen down, that increases the capture of solids because as solids hit that grid, it starts building a mat. And when it builds that mat, now you can start filtering out even smaller debris and smaller debris. So as you slow down the grid, you can increase your capture rate of solids on that core screen, further improving your removal of solids and ensuring that they don't go downstream. And the last thing is the VFD cost and reliability. VFD technologies have improved greatly. They don't take a lot of room into your panel. They really generate very little heat. And what we like to also use VFDs for is to be able to provide overload protection from the power and current monitoring that occurs with the VFD.
Great, thanks, Randy. You kind of teased some of the design of the guide links and the chain and the seals, and I think this attendee's delivering with a question on that. Their question is, units that are rebuilt after years of service, what happens to the seal and its tolerances, and do you replace the UHMW chain in the rebuild process?
Yeah, that's another good question, Jay. So with this ultra high molecular weight polyethylene, this does not wear. What is going to wear is this stainless steel channel. That's what wears over a period of time. When screens come back after 15, 20 years of operation, even if it's in a heavy grid environment, what we see is very little increase in the tolerance. It might increase from 0.5 millimeters to 1 millimeter over that period of time. So for water applications, we see 100% of our screens maintain that 0.5 millimeter. So in summary, a majority of our wastewater screens maintain that 0.5 millimeter tolerance over the life of the screen. It's only in heavy grit environments where we may see it increase slightly, and in water applications, we don't see any decrease in the tolerance.
And here's a question that just came through from an attendee that kind of relates to that, I think, so it might be good to address now. They ask, are there sprockets or guides in the bottom of the screen below the water to guide the chain?
Yeah, that's another good question. I showed that briefly on one of the pictures for our system. If you recall in the animation, there was no sprockets. There's no sprockets. Our chain, our guide chain, and the rail that it rides in, the channel it rides in, is all the way around the screen. So it's water lubricated, very low friction system. There's no rotating sprockets, no bushings, bearings, nothing under the surface of the water. That is really one of the keys as to why our screen is such a low maintenance and has such reliability.
Here's another question that just came through as well, and it's regarding head losses across the machine. They ask, how does the center flow screen handle head loss and pressure build?
Yeah, it's another good question. That's an area that as I talk to engineers and to clients, I make sure I mention that in the common pitfalls when designing systems, and making sure that you can design your screen to withstand the maximum structural loads that are occurring if you have a design that can create maximum differentials across the screen. That's another area with our screen design. If you contact us, we can show you how that grid is manufactured, how it's designed, but it has intermediate supports, and those intermediate supports are what actually hold that grid in place. It's supports that are connected to the axles that are then connected to the chain that provide that ultimate support and strength for that grid. Under higher differentials, we can change the thickness, we can change the materials of those supports to increase the strength of those supports and minimize the deflection. So we've done that several times. We have one installation in Australia for BP where we actually designed the center flow band screen to operate under a differential of 13 feet. Our standard design is 48 inches. That's our standard differential for both static and dynamic design. Other screen manufacturers can only design their screens to about 20-inch differential, and that's really a function of how their grid is designed and how it connects to the sides of the chain.
Great, and as I think we're coming up on time here, I've got a couple more questions to work through, so we'll invite people to hang in there and certainly more questions as they come across. The next attendee asks, how do you control the operating speed of the screen?
Yeah, as I mentioned, that's another good question, Jay. As I mentioned about the VFDs, and the VFDs can increase and decrease the speed of the grid. Those are all controlled by the level detection equipment. So you're either going to have just an upper level sensor. We recommend using an ultrasonic level detecting system, or we also recommend using a differential because we like to operate the screens on differential. So you have the differential, you get the signal which tells you what the differential across the screen. You set your system up so when it reaches a set point, it turns the grid on. When the grid starts to rotate, starts removing the debris, the head loss starts lowering. If you're under a heavy flow, heavy load, and that head loss continues to increase to the next set point, then the VFD will increase the grid speed. Typically, our grid speeds are 4 to 16 feet per minute. But we can run higher in excess of 20 feet per minute. I mentioned the British Petroleum screens that we sold down in Perth, Australia. During our factory acceptance testing, we were actually operating those screens at about 35 feet per minute. So it really provides that operational flexibility again. So it's a differential level sensors providing a signal to VFDs, and the VFDs control the grid speed.
And one last question that came through, you mentioned BP, and I think they're talking about that sort of application where they ask seawater installations for a desalination plant. How is Hydro-Dyne positioned for saltwater desal plants?
Yeah, Hydro-Dyne, we believe we have an exceptional quality screen for those seawater applications. We can manufacture the screen out of stainless steel, and in those situations, we actually have designed, and for the Perth, Australia system, we designed an impressed current anodic system where we can control the corrosion that would occur in that seawater environment. Or we can manufacture the screens out of specialty metals that are specified for high salinity environments. We've done a lot of designs. We worked with a lot of engineers on designs and provided design information for various seawater intake systems. But unfortunately, in a lot of cases, when those projects come out, the contractor is the one that gets to decide which screen manufacturer they select, and all they need is any screen manufacturer saying they can meet the specs. So unfortunately, we have a limited install base because it's difficult to create the condition where that contractor doesn't have the flexibility to choose whoever they want.
Randy, that was our last question. Thanks for rolling through all of them. I think it's a wrap.
All right. Well, Jay, thank you for your help. Appreciate it. And again, thank you, everybody. Please contact us. We'd love to hear from you.